So, any question on what we did this morning? I don't know if you had time to look at it again, but so I wanted to show the example of the swing up again with the direct allocation now. And I don't know if you remember the previous one with multiple shooting. So that was the time grid. It's always the same story. So input is piecewise constant. That's the discretization initialized at 0. Yeah, the graphs are actually not in the same order as before, but so you have your angle here and angular velocity and velocity and position of the cart. And so what we had with multiple shooting before is we could initialize the nodes on, I don't know if you see the time grid, it's quite light, but you have this vertical line, so you could initialize the states, discrete state on all of these lines. But now we can actually even initialize all of the points in between, and you have, so it's case 4, so you have 4 points in between in your trajectories. They're not visible yet, but they will become visible when the trajectories are moving. So you can initialize your trajectories, your states, even in a finer way than with multiple shooting, because you have all these variables, all the thetas, which essentially are your states at different time instance in the trajectories. So if you start iterating, so first, okay, maybe the problem starts feasible in terms of the terminal constraint. So I pretend I hit the target even though the trajectory itself is not physically meaningful. And that will remain feasible throughout because this kind of constraint here is linear, and that's the last theta in the list being 0 essentially. And also it will stay there, Newton will not change that. So you see the trajectory essentially clamped between the boundary conditions and the shape being modified by the NLP solver. Now you start to see the black dots over the red line. So the black dots are all these discrete states actually. So you see that you really have a dense amount of discrete states inside your trajectories. Yeah, so after a few iterations, you start getting something that is more or less optimum. So with direct allocation on this problem, you get pretty much to the solution in 8 steps. After that, it will not change much what happens in the solver. Okay with that? Yeah. So if you remember in multiple shooting, the problem was slightly different. I think I don't have the input bounds here. But the multiple shooting was 10 steps, I think, to converge. And this is a tiny bit faster. And you'll very often see that with direct allocation that you converge often a bit faster than multiple shooting. And that's an effect of lifting, actually. I don't know if I used this word before, but essentially you have more variables to represent your problem, so more states inside your trajectories and with more constraints. And as a general rule, if you don't do anything stupid when you do that, the more variable and constraints you put in your problem, the more linear they will become if you decompose the problem properly. So direct allocation has somewhat more linear constraints than multiple shooting, and it tends to converge faster in terms of the number of iterations at least than multiple shooting. Maybe a few words on the details of how you discretize OCPs with direct allocation. So again, that's the starting point, your OCP, possibly with some boundary conditions and other kinds of constraints. So concerning the inequality constraints, now since you have more states inside your NLP, not only the xk's but also all the states in between, in principle you can impose your inequality constraints on every of your points in the time grid. In theory, you could even say or calculate the trajectories on any point you want using the polynomial interpolation and put the inequality constraints on them as well. So in that sense, you could you can impose the constraints as densely as you want without doing anything special in your formulation. However, it's quite common to impose them only on the main TK, so the main time grid. It's often sufficient to do that for practical purposes. And it's still a good idea to not have too many inequality constraints. Each new inequality constraint you add in the problem will tend to make it a bit heavier to solve. Yeah, but in principle you can impose it on all these time points without doing anything special. Same story as what we discussed in multiple shooting. It's not uncommon to approximate the Lagrange cost by just some very basic rectangular quadrature. And if you want to make it more accurate, you can also carry the L inside the integrator, as we discussed in multiple shooting with the dynamic extension. You just have to be careful if you want to be finer than this. So that would essentially be evaluating L on the first theta, and then pretending that L is constant over this interval and taking this area as opposed to the whole thing. So just presuming that this would be L in this graph. You could be cleaner on saying I'm gonna use a rectangle for every piece I have in my time grid to be more accurate, but then you just have to be careful that the rectangles don't all have the same width because the time grid is non-uniform. So when you do this kind of integration rule, you would have to be careful about this weights that you put. So you always have like the TK I plus 1 minus TK I, and that would give you different sizes. But if you care about accuracy, the easiest is just to throw the L inside the integrator and let it handle this problem. If you have quadratic running costs, so the Lagrange cost, if L is a quadratic function, it actually turns out that you can convert this integral into actually a quadratic form on the thetas, and that's coming from these nice rules on the polynomials being orthogonal. And this thing is also like essentially block diagonal, so you don't destroy the sparsity. So some people do that when they are dealing with quadratic functions here. But yeah, that's a bit of a detail. Okay with that? Yeah. So maybe just a comment on nomenclature. When people talk about direct collocation, they often refer to it as a fully simultaneous optimization technique. And by that, they simply mean that both the integration and the optimization is handled together in the NLP. So both things are done simultaneously. Multiple shooting is often also called simultaneous. Sometimes people say semi-simultaneous technique because only not the whole integration is inside the solver, only these discrete states. But you still have some kind of simultaneity between making the trajectory physically meaningful and making it optimum. And if you go into single shooting, then it's not a simultaneous technique. That's what people would mean by that. Yeah, I actually mentioned that in the beginning already. So each of these theta ki, they have the size of the state. So they are vectors, all these guys. So if you try to use indices to refer to specific theta, so say the theta for the first state in the second shooting interval, third time points, you're talking about an indexing at 3 dimensions. You think of MATLAB, you could not store these guys in a matrix, for example. You would need something like maybe a 3-dimensional matrix or something. So handling these variables in the computer and indexing them properly is not completely trivial. Yeah, and like software like Kpd, for example, that's one of the powerful things you can do, that you can have very high-level indexing of variables, which makes them fairly easy to manipulate. You can simply think, for example, that once you get your solution, you want to plot that, so you need to extract from this long list of long structure of numbers, you need to extract each state at different time instance and make sure that you access the right number in your structure W. So that's not completely trivial. Yeah, that's okay. Something that you can easily do in direct collocation. Because we always discussed a piecewise constant input, but obviously you don't have to choose that. You can also, for example, imagine that in each of this time interval you actually represent the input by a polynomial itself. And why not using a polynomial of this form, right? So then what would happen is that on every of your time points here, you would have a different input, as opposed to have something constant throughout the TKTK plus 1. So you can refine easily your inputs and, for example, pin a polynomial on them. It would actually have one order less actually than the one of the states. That's maybe not trivial to understand, but so the polynomial you have for your states, you need k plus 1 points to represent it, because you also need to enforce continuity between the polynomials. So you need to bring that point together with that one in some sense. You don't need this extra degree of freedom in the inputs, because the input could be discontinuous in principle. So you have one degree less. That's actually something you can easily spot in the constraints themselves. So if you think of your collocation constraints, so you have the one that essentially assigns the theta to the initial conditions on the interval. And then we had the constraints describing the OD or satisfying the OD on the other time points. And the UK is piecewise constant, so it's constant on this interval TK plus 1. But if you were to have a polynomial that for the input u in that interval, where you would place it in these equations would be essentially by saying my inputs in the interval k, they can also change for the different for these different times. And you can readily see in the equations that so the I in this guys goes from 1 to k. So you never have a UK 0. You don't have a UK that, or a U that corresponds to this guy here on the first checkpoint, because this checkpoint is meant to just enforce continuity between the intervals. So you have 1 degree less on this polynomial. But yeah, in your collocation code, if you want to have essentially your inputs represented by a polynomial on these intervals, the only thing you need to do is create more variables for your input and allow a different one on each of these checkpoints, as opposed to keeping the same one when you want to go piecewise constant. You can do that. It's not necessarily, you will not necessarily gain much in terms of optimality by doing that, and you may actually make your problem a little bit less well conditioned. And I'm talking about the linear algebra here. You would tend to make it a bit harder for the linear algebra solvers. Yeah, and then one interpretation of this degree less is that the inputs can jump between the different intervals. So you could have a polynomial here, and then it could still jump down here and then down here. So there's no reason why the input profile should be connected, as opposed to the state, which is supposed to be continuous. Whoops. Ooh. Okay. Yeah, so yeah, I said that before. The linear algebra can be a bit worse conditioned when you do that. You also sometimes see very wild oscillations of the inputs if you start allowing this kind of freedom. So you may wonder if that's the right way of describing your optimal solution. One reason for choosing piecewise constant inputs is also very practical. Most systems, you will attack them via the digital to analog converters, right? So you would probably physically have to be restricted to this kind of input profile when you deploy the solution on a real system. So That's one practical motivation for this kind of profile. Okay with that? Okay. A few words about the structure in the NLP that you get from direct collocation. And I have a good news here. So when we discussed multiple shooting, one of the questions was if you calculate the exact Hessian, so you get this block diagonal structure. But as we have seen in the integration chapter, computing these blocks exactly from integrators, that's quite nasty. We discussed this like triple pass algorithm with like a joint based and so on. So in multiple shooting, it's really not easy to compute the Hessian of the Lagrange function. It turns out that if you use direct collocation, it's actually trivial to compute the Hessian of the Lagrange function. I can show you why quite easily. So again, the Lagrange function would be made of that. This would typically have the right structure, so that's not a problem. That's easy to compute. The problem is in the equality constraints where you have all the dynamics, and when you compute the Hessian, you have to compute these terms here, and especially this one that is very expensive to compute in multiple shooting. But now what happens since all the constraints are in the NLP solver, so your G is a large function that reads like this. And now what changed from multiple shooting? If you remember multiple shooting, so you essentially don't have these guys. They are hidden inside the integrators. And you just have the shooting gap constraints. And the problem is that these constraints in multiple shooting, they are given by the outcome of a simulation. So they are basically given by functions that you cannot write explicitly. They are computer codes. They are not like expressions that you can write on the board if you want. But that has changed now completely because so this is a linear constraint. That's an interpolation. Now that's a linear combination of the thetas in the interval 0. Same for here. And these guys, this is just a sum or like a weighted sum on thetas. And that's your ODE model. And that's typically a bunch of expressions that you have. You can write them down on the paper. So there's nothing in this G function that you could just not differentiate by basic calculus. There's no longer a computer code hidden inside here. It's just regular expressions. Which means that when you want to form the Hessian of this term, you're talking about the Hessian of these guys here. Remember, anything linear disappears from the Hessian. So this would actually also go away. And we have this constraints for this lambdas for the integrator constraints. And so it boils down to taking the Hessian of these terms. And again, F is a bunch of expressions, typically, if it's a classic model made of algebraic expressions. And so you just need to evaluate these terms here, essentially. And as for multiple shooting, this is very sparse because this F is function of the thetas, and these W's contain the thetas. But so if you go off diagonal, essentially, or off the block diagonal, these terms will be 0. So if you plot, for example, this matrix, we saw that in the Newton chapter, that's without inequality constraints, you would basically deal with this kind of matrix to factorize Hessian of the Lagrange function and the Jacobian of the constraints. It looks like this. That's the Hessian of the Lagrange function. It's block diagonal, very, very sparse. And these are well, this one would be the Jacobian of the constraints. And it's also very sparse. It's not exactly block diagonal. No, it cannot be. But it's very sparse, very banded. So that's the same story as multiple shooting. If you give this kind of matrix to handle to state-of-the-art linear algebra solvers, they would have really no problem working very fast with this kind of matrices. It's very structured, even though it's pretty big. Okay. With that, is that okay? So generally speaking, because the Hessian of the Lagrange function is very easy to compute in direct collocation, when we have slightly difficult problems to solve, like quite nonlinear, we tend to prefer to work with direct collocation because you get this Hessian for free. You're working with an exact Hessian, and that's helping your NLP solver as opposed to using approximate Hessians. So if you work in multiple shooting, it's a bit trickier to compute the exact Hessian. And if you rely on inexact Hessians, then you kind of slow down your convergence. So that's a good idea to use collocations for difficult problems. You also have the effect that all your constraints in the problem are closer to being linear, closer than in multiple shooting. So that's also something you gain. Okay, now just as a passing comment, I will not dive too far into this, but just to show you this thing, because we saw, we started from here actually to explain direct collocation, and essentially that's if you would deploy collocation-based integrators inside multiple shooting, and we had this picture where you have Newton schemes operating at this level of the NLP solver and then inside the integrators. And that's one way of doing it. And if you move to direct collocations, you bring everything into the solver. So now the NLP problem has this form with the Kkt conditions with all the constraints together in G. But at the end of the day, actually, if you look at all the constraints you have to solve in direct collocation, or all the constraints you're solving in multiple shooting plus collocation-based integrators, you're talking about the same constraints. That's the same equations that you're solving. This one has, in the NLP, less variables, and then is also handling some variables inside the integrators. And as we said before, you can in principle parallelize the operations inside the integrators, right? You can handle all these blocks in parallel because they are not connected per se. They are connected inside the NLP solver. On that side, you have more variables inside the NLP, and you perform the integration in there. So it's really not obvious how you would parallelize the operations that handle the integration in some sense in the direct collocation approach. So parallelizing this, the steps on this side is really not obvious. And there is this observation in practice that if you deploy a multiple shooting scheme with direct collocation-based integrators, it typically does not converge as efficiently as direct collocation. And that's not always true. You have counterexamples, but it's a common observation that if you do that, you tend to converge a bit faster in terms of how many iterations you need to get to the solution. But all of this is not entirely true in some sense. So I briefly mentioned some work done to show that actually these two things, you can relate them in some formal way. Because again, you solve the same equations on both sides, you just approach them differently, either by kind of a divide and conquer approach or by a like brute force approach, everything at once. So if you solve the same equations in principle, you should be able to do the same things on both sides. It was just not obvious how, but yeah, there are some papers explaining how. And the trick essentially to reconnect these two things, what is really different between them, so the equations are the same, but what is really different is that in some sense there is a bit of a lack of communication between the NLP solver and the integrators because you divide things in this kind of hierarchical structure. And this lack of communication is what makes the convergence a bit slower. Whereas here everything is at the same level, so everything communicates very well via the sensitivities and the Hessians. So essentially you can make very, very simple modifications on this scheme here to make it behave exactly like direct collocation. So the same convergence, it will be the same Newton steps actually. But what you gain in this procedure is that you keep this nice structure where you can parallelize these operations. So essentially, it's basically a way of showing that you can of course, also parallelize the operations inside the NLP solver for direct collocation. It's just not obvious how you do it, but it becomes obvious once you understand this connection. So just a passing remark, but it's a bunch of not very old papers, so this was not discovered very long ago. Yeah, there's a systematic parallel linear algebra for direct collocation. The bad news is that this is not implemented at a very mature level, so I cannot really give you a software that does that. So, okay with that? Yeah. Okay. Can move to the next topic. So we'll talk about interior point method. So we were like kind of jumping around a little bit in this map of optimal control yeah, it's not completely obvious in which order one should proceed, so you have to make some choices. So we discussed the SQP last time. We've been hiding what's happening inside the QP solvers. We discussed the Kpd conditions and how they relate to optimality. We discussed shooting methods yesterday. We discussed collocation today. So now we're kind of covering most of the blocks. I want now to talk about this one. And so I showed you how SQP is dealing with this kind of corner problem in your Kpd condition, and is doing it by just dumping the problem to the lower level inside the QP solvers. Now I want to show you one way of dealing with this problem using interior point method. And essentially that will just really show you how you could approach solving an NLP numerically as a pure algorithm, so without hiding any of the difficulties. So we'll talk about the Kkt conditions again a little bit. So that's the menu for this. So I'll talk again about the Kkt conditions, talk about Primal, interior point methods, Primal dual, and show you a bit how these things work. And so IPOpt is based on these principles. IPOpt is a fairly complex code, but what I want to show you here is that in principle, once you understand how this works, you could code an NLP solver in maybe 1 hour. It's as simple as that. What is complex is all the heuristics that you put around it to, have like, safety barriers, what happens when things go wrong, how you recover from that. So IPOpt has like 10 years of development around this, but the method itself is very simple. Okay, so let's get back to this picture, the Kkt condition. So remember, the NLP problem, cost, equality constraints. You assemble the Lagrange function with these scalar products, and then your Kkt conditions are given by this. So the constraints have to be feasible. Lagrange functions should be stationary. So essentially, it's the gradient with respect to the primal is 0. You need also your dual variables associated to the inequality constraints to be positive. And then you have this problem here. That's the complementary slackness condition. That is essentially saying that mu and the corresponding h cannot be non-zero at the same time. And remember, this is just a contact problem. Essentially, the constraint cannot push back on the solution if the solution is not touching it. So it's really like, it's almost a physical way of looking at it. The problem in the Kkt condition is because of that corner. Can give you an illustration of that. So when we depict this thing here, and I'm really focusing on one lambda and one hi here when I chart this, and you have to imagine the same picture in many dimensions. Probably a bit hard, but the problem remains the same. And so if I have h on this axis and mu on that axis, so h has to be negative, so only that side is meaningful, and mu has to be positive, and only that side is meaningful. So in principle, your mu's and h can only wander in this sector here because of these restrictions. But this condition here is also telling me that I have to be basically on the border of that sector. So my mu on h, when I get to the solution, they have to be on this on these two lines. Another problem is that I mean, the only thing you can do pretty much with this is apply Newton, or if you want to be efficient at least, to solve these conditions. And if you try to apply Newton on a condition like this, it quickly goes wrong, because you can imagine that if you are moving on this branch of this manifold, you're taking linearizations of this branch to see where this is going, and the linearization will basically say, well, the branch is going over there, and there is no way it can understand this corner here. When you linearize at this point, it will see that you will want to go over there. But at some point, if you need to, as you iterate your W, you need to correct the W's to go from that branch to that branch. Newton will not be able to take that sharp term here. It's a corner, so Newton will always think that it has to go over there and will not understand this branch here. Does it make sense? You can also relate that to all these questions around convergence of Newton. You need sufficient smoothness in your equation in some sense to go through the Newton iterations. So that's a problem. If you deploy Newton on this, it may actually work even if you do it brute force, but you may have problems on a number of occasions. So if you consider a simple example as a scalar example with just W in R, W less than 0, the solution for this guy would be 0, because the cost is pushing you towards this bound. And your Kpd conditions would read like this, fairly simple. So you don't have equality constraints, just this one, dual feasibility and complementary slackness. So Newton would have to handle essentially these two conditions subject to these inequalities. And in this chart, now it's really the real thing. So you have W negative on that branch and mu positive on that branch, and they cannot be non-zero at the same time. So you have this condition on them that describes really this manifold. So the starting idea of interior point methods that actually explains the name is to say, well, if my inequality constraints are a problem, what I could do is just move them inside the cost function. And essentially, the idea would be, let's put a very high price on violating that, and kind of almost 0 price when this is satisfied. And hopefully that will look like a good thing. So we're talking about barriers in that sense. You replace this hard wall by something like a smooth barrier in your problem. So here is how it looks like. You can build different barriers, but one that has some nice properties, surprisingly enough, is to use a log function that looks like this. So you can really imagine the log function. It's going to like minus infinity when you approach 0. So in that sense, minus h when it's approaching 0 makes this log going to minus infinity, and with the minus in front, it's actually going to plus infinity. So this NLP with a primal barrier method, you would rewrite it as minimize the cost and the barrier function. And essentially, depending on your tau, this parameter here, you will build different barriers. So that's this function here as a function of h approaching 0, and that's not allowed. That's for tau is 1. So this barrier function here would look like this. It's going to very high values as h tends to 0. So that's basically creating a very strong penalty for going towards infeasible points. And this barrier will sooner or later beat that function. And so the solution will stop going into the infeasible region. And The trick is that as you reduce tau, this function would look more and more like really the real thing. So essentially zero cost on that side and infinite cost when you want to go to infeasible. Does it make sense? Yeah. So this barrier function is essentially a smooth approximation of the so-called characteristic function, which essentially is zero if you're feasible and infinity otherwise. Though the log barrier is not defined on that side, then you have complex numbers, but it's defined all the way to epsilon before zero essentially. So if we make an example, again like a scalar thing, W and some constraints, -1, 1. Yeah, so you'd write this problem as a cost and 2 constraints, one for the upper one and the other one for the other one. No, it's the other one. This one is for -1 and that one is for the upper bound. Okay. So if you were assembling a barrier method here, so you take the cost, a barrier function on the first constraint, that would be this one, take the minus of h, so W plus 1, a barrier on the second constraint. You could have a long list of barrier functions for each constraint. But now you have simply a cost function to minimize. So you've basically removed the inequality constraints from the problem. Okay, and everything will depend on tau now. And you can imagine you solve the problem for different taus and you get a different solution W. I'm trying to chart that here. So if I represent the cost of my problem, that this black thing here, and the free minimum would be around here. And then I have these two constraints, -1 and 1. So essentially my solution is here, W star. That's what I'm looking for. So if I assemble this cost with barrier, for tau is 1, you get this function here. So the minimum is here. So obviously it's not really close to what I'm looking for. But what's going to happen, of course, is as I reduce tau, this function will tend more and more to be like the one I'm looking for. So for small taus, essentially my solution with barrier will be very close to the true one. Okay with that? So you can ask, so how accurate is that solution? There is a very simple answer to that. It's as accurate as tau is small. So you have an order of tau effect. So the proximity of W star tau, the solution of the minimum of this guy, to the actual minimum you're looking for is decreasing in the order of tau. Divide tau by 10 and this distance will be divided by 10. Yeah, you need the ICQ and SOSC for that to hold. As usual, you almost always need these conditions for everything to be nicely behaved. Okay, then now you have a cost function without any inequality constraints, and you could, in principle, simply deploy a Newton algorithm on this cost function. So now remember, if you were adding equality constraint in this picture, that's easy to handle in Newton, right? It's just an extra set of conditions to satisfy. So what would happen here? If you form the Kkt conditions for this guy, so cost and constraints, you would have the stationarity of the Lagrange function, complementary slackness condition, and the h and mu being signed. What would be the Kkt conditions for this guy? It reads like this. So essentially, it's just the gradient of the cost function being 0, right? The gradient of the cost, and if I take the gradient of this log function, the barrier, it actually takes this form here. It's not obvious to see, but if you do the work, you would realize this. So I have h minus 1 and the gradient of the constraints here with respect to W. And you need to be inside the feasible domain. So in the interior of the feasible domain for these things to hold. So that's the interior point thingy. So what if you take Newton steps on this condition here? Essentially, that's what would happen in the end if you use Newton on this. You would take once more derivative on this guy, so essentially Hessian of the cost. It would look like this. You start having h to the minus 2 times this gradients, and then the gradient of the cost. So you could compute your Newton steps via these equations and take steps in delta W, and that would drive you to the minimum of this blue function of the barrier. Yeah, that's for h affine. If h is nonlinear, you have some extra term. Yeah.
Shouldn't there be a negative sign in the gradient?
In here?
Yeah. Because you have a log of minus h.
I should check that. I don't think so. Because when you differentiate the log, you have also some signs effect. But let me check that. Yeah. Okay. So now there is one difficulty here. It's this h minus 2, and you can maybe guess what's happening here. If your solution is very close to the constraint, that means the h becomes very, very small as you approach this point. And this h minus 2 will become very, very large, right? So essentially inside your Hessian, as you approach the constraint, you will have terms that become extremely large. And that's a little bit difficult for Newton. So the picture is you will basically try to solve your Kkt conditions for tau very small. And by doing that, you will make this term here very large if you need to approach the constraints with your solution. And this essentially means that you have basically a lot of curvature in your function as you approach this, and you can see it visually here. So this is smooth here, but it's like it has a very high curvature. And Newton does not like very high curvature. Newton would prefer stuff that is essentially linear. So this works mathematically, but it's pretty hard to handle numerically in the computer. It's difficult. Okay with that? So you actually still have software that use this kind of barrier methods, and you see papers every now and then around this. But yeah, it's arguably not the best way of approaching the problem. Is that clear, this barrier stuff? Yeah. Yeah, maybe we take a break and then I tell you more about how to fix these numerical issues.